Lesson 2.7, Absolute Value Functions and Transformation. The parent function for all absolute value functions is f of x equals the absolute value of x. Recall we previously learned that the parent function for a slope-intercept equation is f of x equals x. The parent function is the simplest form of that type of an equation. There are some basic things that you need to know. So first, the vertex is the highest or lowest point on the graph. The vertex for the parent function of absolute value equations is 0, 0. Also, for every point xy, there will be a negative xy. So the left-hand side of this graph would be y equals negative x, and we can see that because we have an ordered pair negative 1, 1. We could go left 3 and up 3, so we end up with negative 3, 3. So there's my negative x, y. And then on the right-hand side, we end up with positive 1, 1. And we could go right 3, up 3, and we have our y equals x. Both are positive. So to recap, the vertex is the highest or lowest point. For f of x equals the absolute value of x, the vertex is 0, 0. And for every point xy, there will be a negative xy. New absolute value functions come from the parent functions. They can transform and/or translate. So a transformation means that the graph's size, shape, position, or orientation changes. Versus a translation, that means it's just shifting. It's going to either shift horizontally and/or vertically. So we started off with a parent function, which was y equals the absolute value of x. So now we're going to expand on that. We're going to say, what if we have y equals x minus h plus k? The h is going to translate the graph. Horizontally, and the k is going to translate it vertically. Translate it vertically. So the vertex here is going to be hk. And remember that the vertex is the highest or lowest point. We're going to graph y equals the absolute value x minus 1 plus 3, and then we're going to compare it to our parent function, and I have that one already graphed. So the first thing we're going to do is find the vertex, and that's pretty easy because we said that the vertex is equal to hk. So here's my h, here's my k, so my vertex is going to be 1, 3. And you might ask yourself, why isn't a negative 1? Because in the absolute value we have this negative 1. The reason is because our formula gives us that, or our original equation gives us that negative 1. So if I had, for example, y equals the absolute value of x plus 1 plus 3, then it would be negative 1, 3, because a double negative, x minus a negative 1, would yield that positive 1. So we're not working with that right now. We have our vertex is 1, 3. Next, we're going to plot 2 more points. So let's say that x is equal to 0. So we have y equals the absolute value, negative 1 plus 3. Y equals 1 plus 3, so y equals 4. So when x equals 0, y equals 4. So that will be my next point to plot. So we're going to go up 4. And we know that these types of graphs are symmetrical, so we're going to choose an x value that will fall to the right of the vertex. So let's imagine that x equals 2. Okay, so I subbed in a 2 for the x. Y equals the absolute value of 1 plus 3, so y equals 4 again, but our x value was 2. So we'll go over to our graph and plot 2, 4. And now we can see that we translated the original graph up 3 units, 1, 2, 3, until we get to the vertex of the purple graph, and we went over 1 in order to get to the vertex of the purple graph. Remember that a translation is a horizontal or vertical shift, so the size and shape of the graph doesn't change, just the position. Our graphs can stretch, they can shrink, and they can reflect. If we start off with y equals the absolute value of x, and now we include an a, so we have y equals, I'll put an a in the front, a times the absolute value of x. This a value would determine if the graph decides to stretch or shrink. We're talking about the absolute value of a, so you'll notice that the equations that I have on this graph, the a values are all positive. So if a is greater than 1, it stretches and becomes narrower. So the green graph we have is our parent function. Then we have y equals 2 times the absolute value of x. So that means that it's stretching and becoming narrower. Then we go down to the blue graph. It says if a is less than 1, it shrinks and becomes wider. So a is 1/2, so the blue graph is much wider than the green one. So what would you imagine happens if a is negative? When a is negative, we get a reflection, and that will be our final slide. On the right-hand side, you'll notice I included some examples, and we're working with reflections, and what I want to point out here is that here's my parent function, and this orange-yellow line, if we include a -1 in front of the absolute value sign, we end up with a reflection, but it's a perfect mirror image versus the purple one where we included the -2. Okay, so now on with our example. We're going to graph y equals -3 times the absolute value of x plus 1 minus 2. So the first thing we need to do is identify the vertex, and we said the vertex is the ordered pair HK. So take a moment and see what you think the vertex is. The vertex is going to be -1, -2. The -2 is obvious. The 1, remember it's x minus h, so the double negative is needed to make it a positive. And the graph will open down because the value in front of the absolutes is negative. So then we're going to sub in some values to get some points. So on the far left, we're going to substitute in a -2. So -2 plus 1 is a -1, but when I take it out of absolutes, it's a positive. So that translates to negative 3 minus 2, add the opposite. So y is equal to negative 5, and x we said was negative 2, and that was up here. Now we're going to choose a second value, and let's try 1. So we end up with 1 plus 1 is 2. The absolute value of 2 is 2. Whoops, this is wrong. So then we have negative 3 times 2 is negative 6, and we're going to again add the opposite. So we end up with y equals negative 8. So my ordered pair here is going to be 1, negative 8. So now we can graph because we have our vertex and we have two ordered pairs. So we're going to give that a try and then we'll be done. So I have the parent function in purple, and then the negative 3 with the absolute value x plus 1 minus 2 we have in blue. My vertex that we determined, the points that we determined on the previous slide, and then we wanted to see how it moved. So the blue graph reflects over the x-axis, and that's because we had a negative. It stretches by a factor of 3 because the absolute value of negative 3 is 3, and it translates left 1 down 2 because of my h and my k.